Hello everyone. Today we will discuss about Fourier analysis. Basically, Fourier analysis can be split into two parts: Fourier series as well as Fourier transform. Fourier series basically deals with the periodic functions, whereas Fourier transform deals with the non-periodic function. So we can call Fourier transform as a limiting case of Fourier series. In the limit, period tends to infinity. Both these have two parts. I can call it as synthesis and analysis. I will explain these terms later. First, we will move on to Fourier series. A periodic function can be mathematically defined as f of t plus t is equal to f of t. The simplest periodic functions in mathematics are sin theta and cos theta. I can define sin theta and cos theta are the x and y coordinates of a point in a unit circle. You consider a unit circle, radius is 1, and the angle between positive x-axis and the radius vector is theta. Then if you take cos theta, you will get this length, and this is nothing but the x coordinate if you are considering it as a graph. And this is sin theta, and it is nothing but the y coordinate. So I can treat sin theta and cos theta as the x and y coordinates of a point in a unit circle. And if you move an angle 2 pi around the circle, you will end up with the same point, same starting point. So I can say that cos theta plus 2 pi is cos theta and sin theta plus 2 pi is sin theta. Both have period 2 pi. So sin theta and cos theta can be used as base functions for modeling complicated periodic functions. That is the idea behind Fourier series. Now, I will explain what is meant by period of functions. Suppose you consider a function f of theta equal to sin theta. I already mentioned its period is 2 pi. And if you consider a function f of t as sin 2 pi t, what is its period? When you increase the variable t by t plus 1, you will get this as sin 2 pi t plus 2 pi. Then you will get the same function. So the period is 1. So period is nothing but the increment that you have to make in the variable. For example, if you consider f of x equal to 2 pi x by L, when you increase x as x plus 2L or x plus L, because here already you have a 2 pi. So when you increase x by x plus L, you will get sin 2 pi x by L plus 2 pi. So the period is L. In this function, f of x equal to cos pi x by L, period will be 2L. If you are considering f of x equal to sin nx, where n is an integer, period will be 2 pi, and so on. So period is the value which when added to the variable gives us a factor of 2 pi. Okay, so this is what I mentioned earlier. Sin 2 pi t is a function having period 1. Okay. Now consider two simplest sine functions, one with the period 1. This green one is with period 1. After 1, the function increases itself. Then you consider another function with the period half or frequency 2, that is sin 4 pi x. Okay, so up to 1 you will have 2 waves. Here up to 1 you have only 1 wave. Now consider another function sin 6 pi x, that is period 1 by 3 and frequency 3. Up to 1 you have 3 waves. All these are simple sine functions. Here we modified the frequency or increased the frequency. Okay, now what I am going to do is I add up all these functions, that is combine all the 3 functions. Okay, so I modified the frequency and then combined. The sum of these 3 waves, sin 2 pi x plus sin 4 pi x plus sin 6 pi x, I will get a complicated periodic signal. But still it's a periodic signal with the period 1. And in a combination of different periodic functions, the period of the combination will be LCM of the periods of the individual functions. Here the periods are 1 by 3, 1 by 2 and 1, and the LCM is 1. So the signal itself, combination signal itself, repeats after 1. Okay. Anyway, the combination is also periodic. Even though it is having a complicated shape, the combination is a periodic function. So if you think reversely, you can say that if you start from a complicated periodic signal, there is a possibility of writing it in terms of simple sine functions, right? Now, this is a figure of all the graphs together. Okay. Now, this is the idea. Complicated periodic signals can be formed by modifying and combining simple sine or cosine functions. Now, what are the things that we can modify? What are the things that we can modify in a function? What are the things that we can modify in a function? A function can be basically written as f of t equal to a sine 2 pi nu t plus phi. In my previous example, I took a as 1, phi as 0, and nu I took values 1, 2, 3. But in general, I can also increase the amplitude. This is called amplitude. And I can increase frequency, and I can change initial phase. So after modifying all the three and combining, we get a periodic signal as f of t equal to sigma ak sine 2 pi kt plus pi k. Here I take the most general case, varied the amplitude, varied the frequency, varied the initial phase, then combine all the signals together. Okay, this will form a periodic signal of complicated form. Now, I know the identity sine a plus b as sine a cos b plus cos a sine b. Let me call ak cos phi k as bk and ak sin phi k as small ak. Therefore, I can write f of t as sigma k small ak cos 2 pi kt plus small bk sin 2 pi kt. This is a familiar form you might have seen when you studied Fourier series. But in many of the textbook, there will be a term, a constant term before the sine and cosine terms. And what is the relevance of this constant term? In our argument, the constant doesn't arise naturally. But addition of a constant a0 by 2 with our expression doesn't make any change for our arguments, since a constant will just change the reference level of signal, not its shape. In my example, this orange curve was my signal, complicated signal formed. If I add a constant, that will shift upward if the constant is positive, and it will shift downward if the constant is negative. So the constant will just shift the signal along the function axis. Okay, it doesn't change the shape of the signal. So without any loss of generality, we can add a constant a0 by 2 without definition, and we can write f of t as a0 by 2 plus sigma ak cos 2 pi kt plus bk sin 2 pi kt. Okay. Now, what is the significance of period? I considered a function, base function with the period 1, sin 2 pi t. Then I modified the frequencies, sin 4 pi t, sin 6 pi t, etc. That is why I end up with a function f of x equal to a0 by 2 plus sigma. The summation index I can use n as well. Okay, earlier I used k. Sigma n an cos 2 pi nx plus bn sin 2 pi nx. This argument of sine or cosine is simply because the period is 1. If the period is 2 pi, Then Fourier series becomes a0 by 2 plus sigma n an cos nx plus bn sin nx. Okay, there won't be this 2 pi. If period is t, it becomes a0 by 2 plus sigma n an cos 2 pi nx by t plus bn sin 2 pi nx by t. If period is 2l, it becomes a0 by 2 plus sigma n an cos n pi x by l plus bn sin n pi x by l. In order to understand this, I already mentioned you the function as well as its period. Okay, so if your function is with the period 1, you have to write sin 2 pi nt. If your function is with the period L, in Fourier series you have to write sin 2 pi nx by L. If your period is 2L, you have to write cos n pi x by L. If your period is 2 pi, you have to write sin nx and so on. Okay, so this is the idea behind Fourier series. So Fourier series, the argument of sine and cosine depends on the period of the function. Okay, and all this process you can call it as synthesis. And evaluation of the constants a0, an, bn, you can call it as analysis. So I already mentioned Fourier series have two parts. One is synthesis, synthesizing function. The second one is analysis, because it means the evaluation of constants. Okay, so how can you evaluate a0, an and bn? For a function of period t, we have the Fourier series f of x equal to a0 by 2 plus sigma n equal to 1 to infinity an cos 2 pi nx by t plus bn sin 2 pi nx by t. Integrating both sides over one period, we get 0 to t f of x dx equal to right hand side term by term you have to integrate. And the first term will give a0 by 2 into t. Second doesn't mean second term. There are a lot of terms. Okay, and all these terms with the cos, if you integrate over one period, that will vanish. Okay, because if you integrate a cosine function over one period or two period over three period, okay, if it is an integral multiple of period, then it will be 0. And it is true for sine function also. Therefore, all these cosine terms and sine terms will vanish. I will get a0 as 2 by t integral 0 to t f of x dx. And one more point is, no need to integrate from 0 to t. You can as well integrate from minus t by 2 to t by 2, or you can integrate from a to b, provided b minus a should be a period. B minus a should be period. So integration should be over one period. 2 divided by t, this is b minus a. If you are taking the limits as a and b, then b minus a should be the period. To find an, you have to multiply the series with the cos 2 pi mx by t and integrate over one period. Then left hand side will be like this. Right hand side a0 by 2 into integral 0 to t cos term plus the other two summation terms will be something like 0 to t cos 2 pi nx by t cos 2 pi mx by t in one term. Another term sin 2 pi nx by t cos 2 pi mx by t dt. There are two familiar equations in trigonometry. Integral 0 to 2 pi or over one period, minus pi to pi maybe. Over one period, sin m theta cos m theta d theta is always 0. Integral 0 to 2 pi cos m theta cos n theta d theta is pi delta mn. Similarly, integral 0 to 2 pi sin m theta sin n theta d theta will be pi delta mn. So, if it is a product of sin and cos with a different period, different arguments, both have same period 2 pi, then answer will be 0. If it is two cosine functions with the different arguments, both with period 2 pi, answer will be pi delta mn. If it is both sine functions, then also answer will be pi delta mn. Okay. Substituting that value, I can write left hand side is like this. Right hand side summation n t by 2 delta mn, because here our period is t. And when you sum over n, due to this Kronecker delta function, this n will get replaced with the m. Final answer is am equal to, this 2 will go to the other side, t also will go to the other side. 2 by t integral 0 to t f of x cos 2 pi mx by t dx. In a similar manner, by multiplying with the sign, you can write bm equal to 2 by t integral 0 to t f of x sin 2 pi mx by t dx. So if you have a function with a period t, the synthesis part is called f of x equal to a0 by 2 plus sigma an cos 2 pi nx by t plus bn sin 2 pi nx by t. This is called synthesis. And the evaluation of coefficients will give you a0 as 2 by t 0 to t f of x dx, an as 2 by t 0 to t f of x cos 2 pi nx by t dx, bn as 2 by t integral 0 to t f of x sin 2 pi nx by t dx. This part is called analysis. I hope it is clear. If it is a function with a period at 2 pi, I will get f of x equal to a0 by 2 sigma n an cos nx. There will not be any 2 pi by t factor because period t is now 2 pi. 2 pi will get cancel, and bn sin nx. And the definition of coefficients will also change. Okay, only in the argument of cos and sine. And you can see that in a0, an and bn, there is a common factor 2 by t. It happens only because we took the initial constant factor in series as a0 by 2. In some textbook, you may see that this factor is just a0. Then the definition of a0 will be simply 1 by t. If you are taking it as a0 by 2, your a0 will be 2 by t integral. If you are taking series as a0 plus sigma an etc., then your a0 will be 1 by t integral 0 to t. So just for making all these in a similar manner, we are taking the first value as a0 by 2. Okay. Now I will give you some useful tips while evaluating a0, an and bn. a0 is integral of function over one period multiplied with some factor. Integration of any odd function from minus a to plus a is 0. Integration of any odd function from minus a to a is 0. So we can write the limit as minus t by 2 to t by 2 also, because difference is simply period. So if you are taking an odd function, then your a0 will be 0. Also an is product of f of x and cos. Cos is an even function. If f of x is odd, odd into even becomes odd. Integrand is again odd. And if you are integrating from minus t by 2 to t by 2, it will vanish. Therefore, I can conclude that if f of x is odd, then a0 as well as an becomes 0. If f of x is even, the integrand for bn becomes odd, because sine function is odd, even into odd is odd. If f of x is even, integrand becomes odd and bn becomes 0. So it will be very easy if you can identify the nature of function. If it is odd, no need to evaluate a0 and an. If it is even, no need to evaluate bn. I'll consider an example. Find Fourier series of a square wave. Okay, square wave. That is, it is defined as from minus 1 to 0, it is 1. From 0 to 1, it is minus 1. What is the period of this function? 1 unit means this thing. After that, it is repeating. So the length of 1 unit is 2. That is the period of the function. In the plot of f of x, for each xy, if you are considering this point, this is minus half. There is a point half. Okay. So for each xy, there is a minus x minus y. Then the function is called odd. Okay, a function is said to be odd if f of minus x is f of x. Here it is not very trivial by putting x as minus x and check the nature of function. It is easy to look at the graph. In the graph, for each xy, if there is a minus x minus y, we can say that function is odd. And here it is true, because if you are considering this point, this is 3 by 2, 1 by 2, and there is a point minus 3 by 2, minus 1 by 2. Okay, so for each pair of xy, there will be a minus x minus y. Now need to calculate a0 and an since function is odd. Calculate bn, direct integration, 2 by t, t is 2, so 2 by 2 becomes 1. Integral minus 1 to 1 f of x sin pi nx dx. This function is piecewise continuous. You have to integrate piecewise. Minus 1 to 0, function value is 1. 0 to 1, function value is minus 1. Integrating sin pi nx, cos pi nx by pi n, 0 to minus 1. Why? Sin integral is minus cos. I am not putting minus sign. I simply changed the limits of integration. Minus 1 to 0, I changed to 0 to minus 1. I incorporated that minus sign in the limits. Minus sign integral is cos 0 to 1. And cos n pi is minus 1 raised to n. Cos 0 is 0. Cos n pi is minus 1 raised to n. So here you will get a cos n pi. Here you will get a cos n pi. 2 cos n pi. Lower limit you will get cos 0. Final answer is 2 by n pi minus 1 raised to n minus 1. Substituting back in the series, f of x equal to constant time is 0, cosine time is 0, sine time sigma n equal to 1 to infinity, bn sin pi nx. Putting values for n, when n equal to 1, you will get minus 4 by pi sin pi x by 1. When n equal to 2, this will vanish. When n equal to 3, you will get this term. N equal to 5, you will get this term. All the even n will vanish. All the odd n will contribute. And you can see that since function is odd, your series contains only odd functions, that is sine functions. Now what is the meaning? If you retain only the first term, minus 4 by pi sin pi x, your graph will be like this. This is the graph of minus 4 by pi sin pi x. If you consider first two terms, that is this term and this term, you will get something like this. If you consider first three terms, it will be something like this. If you consider first four terms, it will be something like this. So if you consider more and more terms in the Fourier series, your series will approach close to the original function. The original function is a square pulse. And if you are considering 100 terms, you will get something like this. Almost a square wave. At all continuous points, it almost converges to the original function. But at points of discontinuity, there is some problem. Right? I will consider another example. Triangular wave. Minus 1 to 0, 1 plus x. It's a linear. 0 to 1, it is 1 minus x with the slope negative. This is slope positive with intercept 1. This is slope negative with intercept 1. This function, if you consider an xy, there is a minus xy. Not minus x minus y, minus xy. So it is even. For even function, bn is 0. You have to calculate a0 and an. When you are calculating a0, you know the definition 2 by t. 2 by t you can write it as 1 by t by 2. So it is 1 by half period. Interval 0 to t, f of x dx is area under f of x over 1 period. You can calculate the area very simply because it is two triangles. Half bh will give you half plus half 1. Area of this function over 1 period is 1. a0 is 1. So first term in Fourier series is a0 by 2. It is half. an is again 2 by t. Period is 2. So that becomes 1 by 1. Minus 1 to 0, 1 plus x cos pi nx. 0 to 1, 1 minus x cos pi nx. Integration by parts will give you result like this. Then an will becomes 1 by n square pi square cos pi nx minus 1 to 0 plus 1 by n square pi square cos pi nx 1 to 0. Substituting the values, an becomes 2 by n square pi square 1 minus minus 1 raised to n. F of x becomes, first term is a0 by 2 half. First term is not a0, it is a0 by 2. Plus sigma n, an cos pi nx. So writing explicitly by putting n equal to 1, 2, 3, etc. Only odd n will contribute, even n will get 0 values for these terms. And again, I will show you the graph. This is retaining the constant and first cosine term. It is nowhere near the triangular function. If you are considering first 3 terms, constant term and first 2 cosine terms, you will almost get a triangular wave. And if you are considering the first 30 terms, it is something like this. If you are considering the first 100 terms, here you can see the summation terms. 100 terms, you can almost reproduce the triangular wave. There is no problem in anywhere. But in our discontinuous function, there is problem in the discontinuous points. Okay, at the point of discontinuity. So I will discuss Fourier convergence theorem. Fourier series of a function f of x converges to f of x at all continuous points, whereas converges to mean of left and right limit at points of discontinuities. So if you are considering a discontinuous function like a square pulse, at discontinuities, this graph will pass exactly through 0, because our function value on the left is minus 1, on the right is 1, so the mean is 0. So at discontinuous points, the Fourier series will pass through the mean of left and right limit. Another interesting point is you can take the derivative or integral of a series. For example, the derivative of triangular wave, you all know it is a square wave. So if you take the Fourier series of triangular wave and then take the derivative, you will get Fourier series of square wave. For example, the triangular wave Fourier series is this one. For square wave, you simply differentiate this one. If you are differentiating, half will give you 0, and then cos pi nx will give you minus sin pi nx into n pi. So 1 n pi in the denominator will cancel. This minus will reverse this order, minus 1 raised to n minus 1. So we can take derivative or integral of a Fourier series. Okay.